Alright, this paper is one by Meta. Meta has come out with a ton of papers in the past, like, month or so. This one is somewhat interesting. It kind of builds a, it's a different approach to Mo, I guess. You'll see whenever I write it out, but it's similar to Mo, a mixture of experts, and they kind of claim that it does better than mixture of experts, and there's some interesting properties that I just want to point out and just kind of make note of. Maybe that's why it does better. But basically, it's how do you have, like you basically have your base model here, but how do you have a bunch of parameters here? Maybe this is like 1.1 billion parameters, and maybe this is like 10 billion parameters. How do you only utilize, let me move this over. How do you only utilize like a part of these parameters here? So like maybe we only want to use, say, 200 million of these parameters at a time and dynamically be able to utilize that. And the idea is, since this has 10 billion parameters and we're dynamically using them, the active memory that you are using on the GPU is only like 1 billion plus 200 million in this case. But the total number of parameters would be 11 billion because you have 1 billion in your base model and 10 billion total parameters that you're loading in, or 10 billion total parameters that are being trained in some way. And the idea is that this will scale better because you don't have to store as many parameters in GPU memory, but you still get the benefit of having a ton of parameters. So that's just Mo and scaling things in general. This one basically is, I mean, it's basically Mo just with just in changed in a certain way. But yeah, let me just show you the. In reality, this doesn't scale as well as one would hope, but yeah, this is the idea that is kind of being worked on right now. How do you scale models without using all the parameters at the exact same time? So I have a bunch of equations written out here. I'm just going to rewrite them and kind of talk through them instead of trying to talk through them over there, because they're not bad. But yeah, first let's write out, I mean, they have their equations here. Basically, they take this memory model, these memory layers, and the idea of a memory layer is like I have an LLM and I need an LLM to memorize facts, like what is the date of this for, or whatever is some facts that it needs to memorize. And the idea is we can store these in tokens, and it can dynamically load in tokens. Maybe this token says, oh, whatever war you're asking about took place in like 1957. I don't know if anything happened then, but let's say it did, then the model can dynamically load in this token. I mean, in reality, you have dense layers, which kind of use it doesn't exactly use one dimension to represent one fact. So this token probably represents a lot more than that. However, that's the idea of this. It's to dynamically load and compute, basically, dynamically load in memory for the model, and to have it utilize that in some way. Just like Mo, where in Mo, you basically have your experts, where different experts handle like a token, and a token is sent to maybe two of the experts, and these experts basically do something with the token to change it in some way dynamically. So you're not utilizing all your compute, you're only utilizing a part of it. So kind of similar ideas. One, you're loading in tokens or whatever you want to call them, basically just a vector. And the other, you're sending it through a different weight matrix. So they're very similar. And they're actually really similar if I write out the equations. So basically, I'm going to write out the Mo equation, the equation they give down here, just in terms of the Mo formulation, and also a feed-forward neural network. Just to show you kind of the differences of all three of them and to show how similar they really are. They, of course, need to represent this in terms of attention for some reason. There was a paper I think I talked about a couple of weeks ago that was similar to this and how they formalized it in attention. But if you take attention, which has a dynamic query key and value, and you convert the keys and values to weight matrices, that's just a feed-forward network. And I'll show you what I mean in a second. So instead of me rambling on about this, let me start writing out the equations. So basically what we have is we have some token, we need to feed it through some feed-forward network, and we get out an output token, where the input token is going to be of dimension n, and the output token is also going to be of dimension n. Usually what you do is you have your token here of dimension n, you have this up block, which makes it of, I'm calling it dimension n or k, you'll see what I mean in a second, but n or k is usually equal to like 4 times n, and then you downscale this to dimension n again. So this is just your normal feed-forward network. Now, for Mo, you basically have your token here of dimension n, and you route it, like you can represent this as essentially n functions, big N functions, and you can think of each expert as being one of those functions, and you just select some number of those according to some router, which tells you which experts to select. Or in case of the memory network, you select these vectors, which would be what your inner space, what this space here is going to be represented as. So now let me write it out. Basically, you have y, which is equal to the sum of all your expert outputs. Y is equal to I, equal to 1 to k, g of x, I, e I of x. So what this is a scalar right here, 1, and this is a vector right here, n. So what this is a, basically you have your gate here, your gate weight, and you have your expert here for token x. So x is our token in Rn, just one token. So basically what we have is we have a sum of k expert outputs weighted by some value. So how do we get these weights and how do we get this gate value? G of x is going to be our gate, which is going to be the softmax of wg, which is our router. So this basically is going to weigh every expert, and this is our input. I guess I'll call this R instead of G. So this here is going to be a weight matrix of size n by n, and this is a vector of size little 1. And basically this will weigh, the output is going to be of shape big N, where big N is the number of experts we have. And basically this is going to give a weight for every expert we have, and what we do is we select the top k of those. So we have an index, which is equal to the top k experts. So the indices of the top k experts according to our router, WRX. And this should be, so that's what we have here. This and this are the same here. This is just without the softmax because you don't need it until you look at the gate. You can just select the top k indices without it to save some compute, if you so desire. So yeah, basically top k indices, which are just the experts with the highest weights according to our weight matrix, our router weight matrix, and our input token. So after we have these indices, which will be of shape, so this is the top k, so this will be of shape k, just integers, so z in zk. This will just be k integers representing the k indices of our experts, and this will be k weights, so we index this by I. This will be k weights, this will be rk, representing the value of the probability of each of these experts, or the likelihood that token x should go through expert I, so some part of that index. And every expert here, EI of x, is some feed forward layer. I'm just going to make this a simple weight matrix, so WI, where this is n, and this is maybe n by n, but it's some function of x, whatever you want that's up to you. So this is what we have. We have a sum of our expert outputs, so every single expert output, or not every expert output, the top k experts according to our index, which we get these indices from our router. We take the top k of those and we send it through those top k experts here. And we sum up the outputs of all the experts weighted by the gated output, so the router output, or the router probability of expert I being selected. So that's pretty simple. Here, that's just normal mixture of experts. Now let's take what we have in this paper here. So I'll write that out. Y is equal to the sum, I equal 1 to k, of g of q I vi. And so this looks very similar to this here. The difference is q is equal to x, so we're just calling the input token a query. And in reality, this is actually like a matrix multiplication, so it's like wq of x. So it's just some transform version of q, but that's not really a big problem. Or not a transform version of q, a transform version of our input token x in some way. Then you send this through a gate. So the gate is the same as over here, looks very similar. And instead of it being a function of your input, every expert, it's just going to be a simple vector. So expert I here is a function of our input, requiring this matrix multiplication. Instead, we're going to have a simple vector, so just a vector here, which requires a lot less parameters. So that's a difference. And I'll show you another difference after I write out the gate. So our gate here is going to be equal to the softmax of k indexed multiplied by q, where our index again is equal to the top k of w, or in this case it's k, times q. That's a k. So this is similar. This is the exact same, except wr, our router weight, is k. So very, very similar. And this is in zk, so it's just an integer index. And this here is slightly different. Notice how we have the index on the softmax output. This here we have an index on the keys. So this will be of shape k by n, and this will be of shape n. So instead, we are indexing the keys, meaning that our output here will be a vector of size k as well, except this vector sums to 1 before you index it, and this vector sums to 1 after you index it. So that's kind of just a choice that you can make. I have seen mixture of experts where you do take the index of the weight matrix instead, and that way the output vector does sum to 1. But that's one difference that they note here, or that's one difference in normal mixture of experts. Again, not that big of a deal. And then instead of ei being a function of x, you have ei, which is just vi. So it's just a vector here. This is the biggest difference. Basically, instead of summing functions of your input, you are summing weight. This is just a static matrix here, and you're taking the index of that. So instead of taking your token and sending it through some number of experts, you are instead saying, I have this weight matrix here, I have this set of tokens, and I am selecting, say, 2 of those tokens, and then I'm going to sum them together to get 1 output. Instead of saying, I'm going to send it through 2 experts, and I'm going to sum the output. So yeah, basically summing mixture of experts sums a function of your input, while this memory layer is just summing stored vectors that your model is going to learn. Yeah, minor difference that probably has a big impact because this is a lot more expressive theoretically than this. However, this requires a lot less memory than mixture of experts because it's not a function anymore. It's just a single vector. So yeah, this is the memory layer. Basically, take your gate, say which vectors does my token want, take those vectors, sum them together according to this weight. So it'll be a linear combination, which where the weights of the linear combination add up to 1, and your weights are just selected from a massive weight matrix, or massive matrix of a bunch of vectors, and you're just summing that together. So that is that, and I want to show you how this relates to a MLP. So an MLP is equal to WD times, I'll do a SILU MLP, WU times X. So this here, in terms of the shapes over here, let me write out the shapes first. This is, again, a scalar. This is a vector. This is summing over k. And there we go. The shapes are written out. This is k, and this is n. So k is basically the indexed weight matrix, where k is our weight matrix with all our, this is our massive matrix of vectors of shape n by n, big N by little n, where big N is either the number of experts, if we have mixture of experts, or the number of memory vectors that we're storing, if we're doing this memory formulation, and they're each of size little n. And then once you index it, you have that of shape k. So in a dense formulation with an MLP, this would be of shape n little n by big N, and this would be of shape big N by little n, and this would be of shape little n, where x is our input, and this is going to be our up projection, this is going to be our down projection. So if I rewrite this out in this way here, I is equal to 1 from 1 to n of SILU of WU times x times WD indexed by I, and this is indexed. So SILU indexed by I and WD also indexed by I along the big N dimension, so along the number of experts or the number of memory layers. We can see that this is very similar. So here we have this, here we have this, and basically this is our weight here, g of q, or in this case x, sub I, and this right here is our just function that we're summing up according to this weight, where this would just be vi, essentially. So it's very, very similar to an MLP, except you are using the softmax activation instead of the SILU activation. Additionally, the second difference is instead of using all n weights here, you are subsetting that and taking k of those weights. So instead of this being a dense matrix multiplication, you take k of these weights and then you do a dense matrix multiplication. So yeah, very similar. And this leads me to think, can you make this network better, their formulation better, by just replacing softmax with SILU? Because this works really well. We know that this works really well. You can't really do much better than SILU. Softmax, on the other hand, if you take SILU in a feed-forward neural network and replace it with softmax, it won't do nearly as well as SILU. So in this formulation, I'm curious if you can just replace softmax with SILU and if it'll do better. Because basically their claim is that you can, their claim is kind of, you can replace feed-forward networks with this memory network, and you can scale your memory. So remember how I said we have this massive memory, k, or in the experts case, it'll be the number of experts we have, where the number of experts or the number of memories, the number of memory tokens we have is massive. I said before, maybe this is like 10 billion parameters large, but you're only using 200 million. The idea is you can replace feed-forward networks with this and only take a subset of those. So if you're replacing feed-forward networks and you have a feed-forward network, I bet the SILU activation function would do better than the softmax activation function. Just a thought, but since the formulations are so similar, that's kind of what I'm thinking here. Anyways, kind of concluding on the formulation that they have this formulation here. This is what they go with. They say the results, basically, their results that they claim show that it does better than mixture of experts when you scale the number of parameters And the only two differences between mixture of experts in this is the weights here, the indexed weights sum to 1 in the memory network, while in your mixture of experts, all the weights sum to 1 because you apply softmax before indexing versus after indexing. And the second difference is instead of having a dynamic expert where your expert is a function of your input, you have a static expert where it's just a token that you're grabbing from your memory. And these are very similar to an MLP, where your MLP basically has static experts or tokens that you're pulling from memory. You're actually pulling all the tokens from memory, and it uses a silute activation function instead of softmax. So yeah, their claim is you can scale this a lot. You can add a ton of tokens in your n dimension here, and you're only indexing k of them at a time. So yeah, that is that. So they mention that, that's there. They mention that this is not very memory efficient, and this is where they start adding some cool tricks to kind of make this work a lot better. So if we have n, which is just massive, I think they make it 1 million. Like that's crazy. That's very large. So if n is 1 million, then you're going to run into memory issues. They say here you like run into scaling issues because these are so large. So what they do is they take, like we have our k matrix here, which we're indexing, k here, right here. K, we're indexing, and this is of shape n by n, so k of shape n by n, big N by little n, where n is your number of, is basically 1 million, and this is some dimension maybe equal to like 128 or something small. The idea is from another paper called Product Quantized Keys, and what you can do is you can represent this as two matrices here, or kind of represent it in this low rank format where K1 is of shape root big N by, let me zoom in a little bit, it's of shape root big N by little n over 2, and you have K2 here, K2 of shape root big N by little n over 2, so same format. And what you can do is you can concatenate these together in a kind of set form. So you basically take like a set product and you concatenate them together, and you can get a matrix, a unique matrix where each part is unique, of shape n by n, which is the shape of the original matrix. Let me show you how you do that. So let's represent this as a set instead. So set of root n vectors of shape little n over 2. Same here, root n by little n over 2, where the rows are going to be, so this is the n over 2 dimension, and this is the root n dimension. So we basically have root n vectors of shape n over 2. So this will be vector 0, this will be vector 1, and this will be vector root n, and same here. This will be vector 0, 1, and root n. And this will be, not m, root n. So this will be k1, and this will be k2. And what you do is you concatenate these as you would probably expect in every combination possible. So the first vector here, the first unique vector, would be vector 0 from k1, and vector 0 from k2. And our second vector here will be vector 0 from k1 and 1 from k2, and you do this, and you get vector 0 and root n from k2, and you keep on doing this until you get your last vector, which is root n, index root n, and index root n, and you get a total of n vectors of shape n little n, because you are concatenating these vectors, which are each of size n over 2, little n over 2. So this is how you have a low rank representation of your full rank matrix that you actually want to utilize. Now in reality, you are just going to have your quantized representations, and you're going to work with those. So they have these formulas over here, which you can utilize instead of utilizing the full rank version. So you don't actually have to actualize this. You just have to work with these two low rank versions of your matrix. So you first need to index. So like the three operations we have here is first index, then compute the gate function. They call this S, by the way. So the gate weight is S. And then the third part is multiply those by the values. So the first part here is I1 and I2. So you want to compute the indices using both K1 and K2. And this is going to be done by doing the top K of K1 or 2 multiplied by Q. And this will be a matrix, which is of shape root n by n over 2, multiplied by your query. You first half the query. So first half your query into two parts, and then you either, so like you have your query here, and you break it into two parts. So you have Q1 and Q2 based off your dimension n. And Q1 is going to go with K1, and Q2 is going to go with K2. So that's the notation here. 1 over 2 is just denoting you do this for both K1 and K2. So you do this for both halves of the dimension. Instead of me having to write out I1 and then I2, which is the exact same equation. So this here will give you a output of shape root n here, root n. So this will give you n weights here. And then you take the top k of those, top k. So you take the top k of those, and this will give you k indices from your first and second k matrices, your routing matrices. So once you have those, you then have to compute your weights. So S1 and 2, which are your g of x or g of q in our case. This is going to be equal to the softmax of K1 or 2 subsetted by I1 or 2, and then multiplied by Q1 or 2. So basically, it's the equation we had above, except you are working with K1 or 2 and Q1 or 2. So K1 or 2 is, again, going to be root n by n over 2. And since we are indexing by the index we found up here, this is going to be of shape K, where K is the top K indices we have, by n over 2, little n over 2. And Q1 over 2 is going to be of shape n over 2 because we are taking a half index, so Q1 over 2. And we take the inner product of these two, and this gives us something of shape K, where K is our weight, and then we take the softmax. So this will give us two sets of weights here, S1 and S2, where S1 corresponds to K1 and Q1, the first half of our dimension, and S2 corresponds to the second half of our dimension here. So K1 and K2 correspond to S1 and S2, and the first and second half of Q. So then what they do is, I think what they're saying here is the combined version of S is equal to just S1 plus S2. So you basically just sum them. I could be wrong, this notation is a bit strange here, but I think that's all they're saying here, is you just sum the values from the two parts. So yeah, lower rank version, which should hopefully do as well as the full rank version. It probably won't, but it should do better. It's at least a lot easier to store in memory, and it should do better than the individual parts themselves. Like instead, if I had, say, 2 times root n and I was utilizing that as my full rank matrix, it should do better than that. So yeah, this is how you do the low rank version of this up here. So same equations, you're just splitting it into 2 parts, k into 2 parts, and working with those 2 parts. And once you have S, your combined S, S1 plus S2, you can just do this last part here, this last equation, which is just summing over k. So that's not memory. The hard part in memory is computing these indices and getting the weights, because that requires full n computation, where n is the number of tokens you have. You have to compute it for every single one. This low rank version only does it for 2 times root n. which is much less than n. So yeah, there we go. Memory efficient computation. So then they say they make this parallel. They can compute this in parallel, and the way they do that is, I was reading this and I thought it was more complicated than it actually is. But basically, you have two parts. Let's say we already have our indices that, like we have our indices over here. Basically, I guess you're going to compute the indices, but basically the problem is we have this massive matrix here, where this is, say, 1 million rows by, I don't know, 128 columns or something small. If you want to put this on multiple, you want to put this on multiple GPUs because you can't store something this large on one GPU. So what they do is they split this massive matrix by the dimension, and they say, all right, we're going to store this first part on one GPU, we're going to store the second part on a second GPU, and so on. So they basically shard this massive memory token matrix onto multiple GPUs. In this case, they have two GPUs, so they split this massive K matrix into two parts. And this K matrix is going to be the one we utilize, so it's not going to be the full rank n by little n, it's going to be the low rank n by n over 2. So you split this into two, which means you're splitting this dimension into two, the little n over 2 dimension into two parts. And basically what you do is you store each part on one GPU. So in this case, we have this massive matrix here, and you store it on, say you store this half on GPU 0, and you store this half on GPU 1. And essentially, whenever you have your indices, you will send some of your indices to GPU 0, and some of them to GPU 1. Or rather, you're not sending a part of it. Basically, you have you basically share these indices with all your GPUs here. So GPUs are sharing these indices here, and then they get the half embeddings. So GPU 0 is going to look at all these indices, A, B, C, and D, and it gets the half embeddings for them. So only the half it stores on that memory. And GPU 1 does the same thing, except it does it for its half of the memory. And then what they do is, after they grab the halves of memory, they, you have these halves of memory for the indices you desire to have, for the indices you desire to have the full embeddings of. Then what they do is, once they have these halves, they share the halves. So GPU 0 has all these halves for all your indices, GPU 1 has all these halves for all your indices. They then share them, and they concatenate them together. So concatenate them after they're shared, and yeah, that's the idea of how they shard it. Basically, you're just storing a part of the dimension, and you send the indices to the GPU, and the GPU will send you back a partial embedding for those indices for your massive K matrix. Here, they mention that instead of, I'll just read it out. So basically, they use a shared pool of memory parameters across all memory layers. So they call these memory layers, basically replacing feed-forward layers with them. And they say that they have a shared pool of memory parameters. So you basically have 1K that you're sharing with all these layers, thus keeping parameter count the same and maximizing parameter sharing. So you have 1K that you're basically sharing with all these layers to kind of minimize the number of parameters you actually need to allocate. They find that multiple memory layers increases performance significantly over having a single layer with the same total parameter count, up to a certain number of layers, in our case 3. Beyond this point, replacing further feed-forward network layers degrades performance, showing sparse and dense layers are both needed. So basically, they only replaced a few feed-forward layers with this because it degrades performance for some reason. And that's probably because you're sharing these parameters across those layers. If I only have a set number of parameters and I share them for every layer, it's not going to be that expressive. So they say that they only have 3 layers that they actually utilize, that they actually put this memory layer in. Here they say they create a custom CUDA kernel to do this, and here they basically say, oh, there's a problem with stability. So if you have this here, this is just going to be your memory layer, or rather, this is like a memory transformer. So this is normal attention here. This is a pre-norm, RMS norm. And this here is the layer that they have, just a fancy way of showing it. And they have a skip connection around that. So like I said, you're literally replacing feed-forward layers with that. So they mentioned down here, I'll just read it. They improve training performance of the memory layer by introducing input-dependent gating with the Silu nonlinearity. The output is this. So basically, they say that the performance isn't amazing if you only have, or you can make the performance a little bit better by adding a full rank matrix here in parallel with your memory layer matrix, where this is just a normal feed-forward network. Like if we just took this part here, this would basically be a normal feed-forward layer where this is like your up projection, this is your down projection, this is your intermediate activation function. So they basically have a small version of this in parallel with these memory layers, which are basically extracting these memories from like 1 million tokens. So they say that that improves performance. They say here that they find for large memory layers, training can become unstable, especially for smaller base models, and they utilize a QK normalization when needed to alleviate the issue. So norming these two parts here. One thing to note is that they use a multiplication here. This reminds me of Mamba 2, what they did there, or maybe it was Mamba 1, where they basically had the normal Mamba part here, and then they had this part off to the side, which kind of did some small computation and kind of acted like a skip connection for some of the information. But it's kind of a skip connection that does a dense computation in a way. It's a bit strange, but yeah, it works because feed-forward layers are all you need, I suppose. So then they do a bunch of experiments, basically trying to show, let me go up to the top, that if they utilize the number of active parameters being used is not that high. The number of total parameters is really high, but as you scale the number of total parameters and you keep the number of active parameters the same, it can end up beating or being very comparable to the baseline. So in this case here, this is the negative log likelihood versus the memory size. So this is the total number of parameters. So the total number of parameters, which includes all, or most of it, are the parameters in this massive K matrix for the tokens you're doing this lookup for. So in this case, they have 128 billion parameters in their sparse model. However, only 1.3 billion are active, and they compare this to a 7 billion parameter model, which is full rank. So I think this is Llama 3 here, and this is Llama 3 just way smaller, and with 3 layers that have this memory lookup layer instead of the feed-forward layer that have access to 128 billion parameters. However, they only select K is equal to a small number of them. So if we look here, as you increase the size, so this is increasing the size, I think this is increasing the size of your memory here. As you increase the memory, the performance starts to go toward a full rank model. So this line here represents the negative log likelihood for our full rank model, 7 billion parameters, while this line here represents the performance of our the performance of our sparse model, increasing the number of memory parameters here. So as you increase it, it nears the performance of a full rank model. However, it utilizes way less parameters than the full rank model. So a lot less parameters that are actually being utilized while you get the same performance. So that's interesting. Yeah, that's what they show here. Whoops. So they also show down here that it scales better than a dense model and a Mo model. So they look at some benchmarks and they show the number of base parameters being used. So this is the number of active parameters being used, not the total number of parameters. And they show as the base parameters increase, the memory plus model, that's what they call it, scales better than the dense and Mo alternatives, utilizing a very large memory. So the base as you increase this base model, it utilizes the parameters it has access to a lot better, apparently, according to these results here. And you can see the same here. So that is that. They also mention that it utilizes less flops and less tokens than a dense alternative. At 64 million keys, so that is this, are the key matrix they have, 128 billion memory parameters, a 1.3 billion memory model approaches the performance of the Llama 2 7 billion model that has been trained on 2 times more tokens using 10 times more flops. So that was the first table I showed above. They also mention that at only 1 trillion tokens of training, the Memory Plus model approaches the performance of the Llama 3.18 billion model, which was trained on 15 trillion tokens. So apparently, it's a lot more efficient at utilizing the data it's given. So that means you train it for less time, and it utilizes those parameters a lot better. So that's interesting. If that is really what's happening, then it could be a new paradigm. Like, this would be very beneficial. You have to train for a lot less time and on a lot less data. It could be overfitting, however, because you have so many parameters here. So that's also something to think about. Maybe it's just overfitting to the data because we have so many parameters that are just sitting there that are being kind of pulled from memory. There becomes a point where your model will start to overfit if you have so many parameters, though on 1 trillion tokens, I don't know. That's something to look at. And then they show here, this is the base model. As you increase the base model, it does better. But in general, Memory Plus does the best overall. This is Memory Plus with 1 million memory tokens. And in general, it does better than the rest of the models that you can try, like a Mo model or a memory model, which is an old version of the Memory Plus model. It does better with the same number of parameters. So this is the number of parameters total. This is the number of active parameters, and in general, it does better. And here, they look at the 1.3 billion parameter case, and they say, well, what if we increase the number of parameters in the memory? And as you increase it, it does better on the benchmarks, as you would expect. So, yeah, good benchmarks as with every paper. And there's a dog barking in the background, so hopefully you can't hear it. But so I mentioned above that they add this gate, this weird gate with a silu around it. In this case, they use a swilu. Ooh, fancy. If you utilize that, it like barely does better. The negative log likelihood stays the same for all the ablations they do, which I kind of find funny. And the other metrics here, so NQ and TQ, a negative log likelihood, like kind of decrease, which I don't know. I kind of find it funny that it just like the ablations they have barely decreases the anything. They're like, yeah, our base is pretty good, and we add a few other things, and it does about the same. Here they basically show that you want to add the memory layers to the middle, and if you add it to too many of the layers, it does worse. It does as good as if you add it to one of them. And then here is if you increase your memory too much, it can do worse. So memory 1 million, 16 million. If you increase it, it does slightly worse in terms of negative log likelihood. But that's also increasing the dimension, so who knows. Wish they would have kept one of those constant. All right, so yeah, that's the paper. I am a little conflicted about the results here. I think there's more to it than they kind of experiment with. I think it's a good basis. Basically, it's taking Mo, and instead of having experts be functions, you have experts be these tokens that you're just summing. You're just summing these tokens, and they utilize basically a feed forward with a dynamic number of functions that you have in your feed forward layer. So I'm curious if there's a lot if there's a lot better way to do this. It the like attention, your Mo network, this network, and a feed forward network, they're all similar depending on what you change. In attention, you have dynamic query keys and values. In Mo, you basically have dynamic queries and dynamic values. In this, you basically only have dynamic queries, and in a feed forward layer, you also only have dynamic queries, in a way. So there seems to be some connection here, perhaps, between Mo feed forward layer and this layer. Maybe there's something that can connect them. Maybe one of them actually does better than the rest, because this paper kind of makes it seem, oh, it's really different from Mo. It's not that different from Mo. You're basically just changing one thing and making the values static instead of dynamic functions. So I feel like there's some middle ground between Mo and this that is good. That's better than both, the better than one of the two. But yeah, I don't know. I think it's somewhat interesting to see how they scale this and to see the improvements that they do. Interesting. It's an interesting approach to scaling models to be very large. So yeah, that's memory layers at scale.